have, I would say, a slightly more packed didactic as compared to the case presentation. We do have a case, but the didactic will be a tad heavy today because we are going to be doing one heavy topic. And the second reason is also we are going to do some hands-on work, which is like a bit of a case study and active participation, but that will again take some time. The didactic first, Bama will get it started with tessellation, and which will be followed by Sendil, who will do math through origami. I hope all of you have a few A4 sheets of paper, as Sendil had mentioned, because there's a bit of hands-on activity and we need that, which will be followed by a short case study by Nikita. Nikita, are you around?
So she'll join in sometime. So she's on.
Sure, no problem. And then wrap up and feedback. We don't quite need the 10 minutes, so we can extend the Nikita's case study to up to 20-25 minutes probably. Yeah. So without much ado, I'll hand it over to Bama.
Thank you, Ramesh. Yeah. So we see like tessellations all around us, especially in like, flooring and tiling patterns. So what exactly is a tessellation? Next. Tessellation is any pattern that is made up of some repeating shapes, and secondly, there are no gaps or overlaps in the patterns. So it covers the surface completely without overlapping or leaving any gaps, and they can go on forever in a plane. So let's first look at the simple of patterns, right, which we see all around us. And these are made up of regular polygons. So regular meaning all the sides and all the angles are equal. So we have equilateral triangles is a regular polygon, and it can tessellate as shown on the left. Similarly, of course, square tessellate, we see it everywhere in tiles. And also six-sided regular hexagons can also tessellate. So how about a pentagon, correct? Why doesn't a pentagon tessellate? So as you can see, we can arrange three regular and the same sized pentagons to meet at a point as shown. And then we have a gap. So why do we have this gap? A regular pentagon's angle is 108 degrees, and 3 times 108 is equal to 324. And which is just less than 360 of the full circle. And therefore the gap occurs. It's quite straightforward, right? And if I keep a fourth pentagon, it must overlap because 4 times 108 is 432, and which is greater than 360 of the circle, as shown in the second figure. So this actually tells us very clearly why some regular polygons tessellate and some don't. And so we have to think in terms of interior angles. And at every vertex where the polygons meet, their interior angle should add up to 360 for the polygons not to overlap and not to have any gaps. So basically, if a single regular polygon has to tessellate, the interior angle, right, should be a divisor of 360. So just look at the equilateral triangles. And if you look at the red dots in the center and also above at the table, if we divide 360 by 60, it is 6, right? 6. So that's why we have 6 equilateral triangles are going to meet at a point. And similarly, a square, if we divide 360 by 90, it gives us 4, which means 4 squares are going to meet at the point. At every vertex, you're going to have 4 squares meeting. Similarly, a hexagon is again divides 360 and by 3. So we get 3 hexagons are going to meet at that point. So as you can see, right, pentagons and octagons, interior angles are 108 and 135, and these do not divide 360. Right? So therefore, we have only 3 regular polygons that make regular tessellations. So forming a tessellation with a single regular polygon, it's also called a regular tessellation, and only 3 such polygons are possible. That is the triangle, the square, and the hexagon. And tessellations that are formed by 2 or more regular polygons, and of course convex regular polygons, and in the same order, they surround the polygon vertex. And these are called semi-regular tessellations or even Archimedean tessellations. And there are just 8 such tessellations. And they are made up of 2 or more types of regular polygons of the same side length, of course. So let's look at some more of these in a little more detail. And the first one, right? Again, just look at the red dot where I have put. You can see that at every vertex or at that red dot, right? We have a square, an octagon, and another octagon. Okay, meeting in the first one, the first tessellating pattern. And these, so we, the way that we write this is 4, 8, 8. A square means 4 sides, octagon is 8 and 8. So this is how we define the tessellation in this format. And of course, the interior angles, they all add up to 360. And similarly, the next one, we have a square, a hexagon, and a dodecagon, right? And which is again denoted by 4, 6, and 12. A dodecagon has 12 sides, so 12. And the interior angles, the sum again adds up to 360. And the third one is a triangle, again and 2 dodecagons, and they again add up to 360. And for this, we just have to give the children, several regular shapes and ask them to produce the patterns. We should not show them this, right? It is an exploratory activity. Ask the kids, how can you make these polygons tessellate? And then the fourth one, this is actually found, the styling is found in the Archaeological Museum in Spain, in Seville. And I've tried to make the same design using 2 squares, a triangle, and a hexagon on the floor. And this tessellation is denoted by 3, 4, 6, and 4. And that's the vertex configuration. And over here, you have 2 patterns. Now, both of these, they use triangle and square tiles, okay? And always 3 triangles and 2 squares, but they form very different patterns. And the arrangement also matters. The order in which you arrange the square and the triangle around that vertex, it matters, and it shows how the pattern is going to be spread. Correct? And you get 2 completely different patterns with just 3 equilateral triangles and squares. And this one is 2 hexagons and 2 triangles. They tessellate as shown. The vertex configuration is 3, 6, 3, 6. And so what we have seen till now are semi-regular tessellations. They are made with 2 or more regular polygons having the same side lengths. So now let's look at tessellations that use not just polygons as tiles. So this beautiful tessellation of birds has a 90 degrees. It has a 4-fold rotational symmetry. And we'll see how to make these in the next few slides. And before we do that, let's just talk about Mr. Escher, MC Escher, and he passed away in 1972. So he was like, in the last century. And he was a Dutch graphic artist, and he made these beautiful wooden carvings and lithographs. And all his art had a very strong mathematical component. And he not only made these amazing tessellations, but he also made designs that were built around what he called as impossible objects. For example, his creation in the middle, it's called Ascending and Descending, and it shows an impossible flight of stairs where the people are all climbing up, and that's shown on the right. See, if you look at it, it's like, the stairs are always going up or always going down, right? And these are just optical illusions, and they cannot really exist as a solid. And on the left, these are the tilings found in a site called Alhambra, again in Spain. And when he visited this site, he was like, so impressed by these tilings. And then he started creating his tessellations. And these are some of his very famous tessellations. And he didn't want to just, use ordinary shapes. So he started with squares and triangles and all that. But then he made these tessellations like images of birds and animals and people. And he went about it in a very systematic way. Like he started with quadrilaterals like rhombuses and squares, and then he took into account their symmetry and what is the rotational symmetry. Like for example, triangles always have threefold or sixfold rotational symmetry, whereas squares will have four. So so here you can see that the rightmost one, right? He started out with triangles, correct? And then the center, the other two, they've started out with squares or parallelograms and or rhombuses maybe, yeah. And then he used figures to tell stories like, birds evolving from a rigid mesh of triangles to fly free in the sky, and he called it liberation. Okay, the last one. And then the center one, it's called predestination. That's what he has named his artwork, where flying birds and fish are born from the same black and white tessellation. And so now just let us look at how exactly he created them and how we can also do so with our kids. So how do we create such a tessellation? So we'll start with the leftmost panel. So we start with the square and we start to cut, right? The top side of the square, we start at the top vertex, at the right vertex, and then we end up with the left vertex as shown. So basically any kind of pattern, as long as you start and stop with the two adjacent vertices. And then you just slide the piece to the opposite side, and then you put a tape and you stick it. And this is your very simple tessellating tile. And it tessellates as shown. Okay, in the second figure, suppose we start with the hexagonal tile and then we make a pattern cut and we rotate this about this vertex to the next adjacent side. Okay, and then you cut it or you tape it. And this is how you get your lizards. It's what Escher has done. And on the right side, we start off with a square. It can be a parallelogram, I think, also. And then we can create this, flying horse or a barking dog. And so basically, he started off with polygons, and then he modified the sides that involve rotations or translations or flipping or reflections, all based on the symmetry exhibited by that particular polygon, and done very carefully and using your imagination. He has come up with all these beautiful creations.
A quick question.
Yeah.
All these polygons which we choose have to be either a triangle, hexagon, or a square, right?
Not necessarily. Not necessarily.
As a starting point, because when I'm sliding, I'm just wondering whether they have to be necessarily the tessellating regular polygons, which happen to be the 3, 4, 6-sided.
Yeah, no, they can also be things like parallelograms and rhombuses, which are not regular polygons, but still tessellate.
Okay.
Yeah.
Okay.
Yeah.
Yeah, of course, because the combination will help in that. Okay, I got it.
Yeah.
Thank you.
Yeah. Yeah. So this is a simple animal tessellation that I do routinely with kids, and they love it. So you just start off with a square on a cardboard with a circle inscribed in it, and you cut off the opposite two pieces, what we have shown in that maroon, okay, and you slide them along the red arrows to the opposite side, and then you tape them, and that's it. This is your tessellating fish tile. And using this tile, you can place out as many fish as you want, right? And you can decorate your fish as shown. And this has translational symmetry, of course, which means that I can move across the tessellating plane in any direction and the pattern repeats. So here I started off with an equilateral triangle, cut out a simple symmetrical pattern on the three sides, and this is my tile. I can then use this tile to draw the pattern as shown in the center and color it up like, as a bird or maybe like a shell or whatever, the child use her imagination and do so. And this has a six-fold rotational symmetry. So now, till now, like whatever we have talked about is what we can do as children's activities in tessellations, to improve their visual skills and all that. And then last year sometime, Ramesh shared this eye-opener video about the recent research in tessellations, and it opens up a whole new dimension to the idea of tessellation itself. And I thought, like, I can share it with you teachers because, you can appreciate it and whatever I've understood, that is. So this type of tessellations here, instead of starting from the center and going outwards, another way we can define a tessellation is to go from the outside to the inside, right? Creating more and more details similar to what we do in a fractal construction. So Sir Roger Penrose, he's a very famous mathematician, and sometimes in 1970s, he started with the regular pentagon. Correct. And he observed that a regular pentagon can be packed like a flower arrangement with 6 smaller pentagons as shown in step 2. And this packing sort of really, it leaves some empty space in the original pentagon in the form of, 5 isosceles triangles. And we can repeat this pentagonal pattern as shown in figure 3. And figure 4 just shows that red area marked in figure 3 that is enlarged. So what I've done here is each of the 6 pentagons are replaced by 6 smaller pentagons, correct? And then the isosceles triangles, they become rhombuses when they join together, okay? And then in the center, the rhombuses, they grown into like some spiky shapes. And inside this, Penrose could fit in 1 more pentagon. Correct. So basically, he divides each into a pentagon, a pentagram, that is your star, a half pentagram, or a paper boat. Yeah, that's about it, right? And then if you use the substitution rules like shown on the top, we can tile any plane with this. So this is how the plane is being tiled. Okay, it looks beautiful, and how each generation evolves. And when each pentagon is now going to be replaced by 6 pentagons, and the other substitution rules are also followed. Oh yeah, it has a rhombus also. The tiling pattern has got 4 shapes basically. It uses 4 shapes. It uses a pentagon, a rhombus, a pentagram, and a half pentagram, or the boat. And here's an actual floor tiling made with this tessellation. You can see the 4 shapes. And what is really magical about this tiling is, even though we use only these 4 regular simple shapes, regular meaning not, yeah, 4 simple shapes, yeah, the pattern never repeats. Okay, and that's the amazing new discovery that Penrose came up with. He called it's called aperiodic tiling. That is a non-repeating tiling pattern. And and he now simplified it. Okay, he now used only 2 tiles. He used a fat rhombus and a thin rhombus, and with these two, just with these two, he managed to create aperiodic tilings. There's tilings that never repeat themselves. So previously, what all we have seen, they're all periodic, right? That is, after a certain time, they just repeat, but these don't. Until then, previously, it was believed that if you used a fixed number of shapes for tilings, right? We used only a square and a rhombus or a square and two octagons or something. The tiling has to repeat, right? But here, Penrose has managed to create a tiling that doesn't repeat. That means it has no translational symmetry, and with just two shapes, right? So you can imagine if you're standing on a square that is on a floor, say, that is just made of square tiles, say, you start walking, and after a particular point, you know what the rest is going to be. Over here, though, how much ever you walk, how far ever you walk on this kind of a floor, right? Whatever information you've already accumulated, you still can't predict what happens next. You can't, it will be something that you've not seen before. So that was the beginning of realizing that we can have non-repeating patterns that are still very structured. And so he captured, Penrose became really famous because of this. First, he has found a way to generate infinitely changing patterns using just two types of tiles. And even more spectacular, the tiles are very simple. They are symmetrical shapes, and by themselves, they had no, unusual properties. So he made several versions of this aperiodic tile sets, and one of his most famous ones was the kite and dart. And the basis for these, again, he started with the regular pentagon, and each one has got two simple symmetrical arcs, the blue one and the red one. Okay, and then he established a legal placing rule. He said, when you join the tiles, the arcs must match up, right? They must create contiguous curves. And without this rule, kites and darts, they can, if you place them, they repeat, the pattern repeats. But with this rule, that is the, the red and the blue arcs, they should be contiguous. New variations keep creeping in and repetition never happens. And the different ways in which the kite and the dart can be placed together is seen on the top. And they form contiguous curves, and the pattern never repeats in whatever direction you'll go or you look at them. And so this is some intuition as to why these tiles form this infinite non-repeating pattern. And in some of the previous sessions, with Fibonacci numbers, we learned that the pentagon is very closely associated with the golden ratio. That is phi, which is a very irrational number, correct? So the ratio of the diagonal of the pentagon to the side is phi. And since the kite and the dart are actually sections of the pentagon, right? The kite and the dart, they have, the golden ratio built into their construction. So the ratio of the lengths of the longer side to the shorter side of the kite is again, and the dart is again phi. The ratio of the areas is again phi. And if you take the large area of the kite and the dart tessellation, or even the number of kites to the number of darts, okay, in any large area, it is going to approach the golden ratio. And so since phi is a very extremely irrational number, and that's the reason that the pattern doesn't repeat and it is aperiodic. If this ratio had been a rational number, then the pattern, could have been said to be periodic, but it is not. So here on the right, we can see that the kite and the dart again can be, substituted by two smaller kites and two dart halves. And dart can be replaced by a smaller kite and a dart. And if you do this kind of substitution an infinite number of times, this is how the pattern you get. Suppose you start off with this kind of a, the pattern what we call as the sun. And in nature, we see that hexagonal tessellations like are in honeycombs of bees, like shown in the right, top right, and the snake skin, it is a kind of tessellation made out of a rhombus-like shape, right, bottom right. And these are periodic. But do aperiodic tiling pattern occur in nature? So Penrose thought it was not possible, it is unlikely, but it was found in aluminium manganese crystals by Dan Schreckman. Till then, all crystals were thought to be periodic. Crystal, you know what a crystal is, right? A sodium chloride crystal is going to have, it's like a works of a cube, many cubes together, put together. So the alternate sodium and the chlorine atoms, they are just going to be alternate on the vertices of this cube, and the pattern repeats. But these crystals, this aluminium manganese crystals, they are aperiodic, and they were given a new name called quasi-crystals. And they look very similar to Penrose tilings. If you look at it, they seem to have some kind of a pentagonal pattern. And so, yeah, both Schreckman and Penrose both got the Nobel Prize for this. So, there are a number of amazing sites that explore tessellations, and I've listed some of them here. And there are the YouTube videos about aperiodic tiling is also listed. So like this, math is filled with, so many fascinating topics like factors and tessellations. And so it is good if we can include a little bit of all this into the syllabus, so to speak, and, so that, we can just open up a child's imagination, make the child fall in love with the subject. And I think then our job as teachers will be done. So, yeah. Thank you. Ramesh, you're muted.
No, every time we hear of it, it's so truly mind-blowing, this whole tessellation thing.
Yeah.
It's amazing how, whether it is Escher or Penrose, I mean, it's unbelievable.
Yeah.
Persia and all were not at the leading of all these things, Mama.
Yeah, they were also supposed to be, but then somehow all the examples I could get were from Spain. I don't know why. So
yeah,
stylings. Yeah.
Because some of the art looks so Islamic art, no? I mean, where Persia was leading the way in some of these things, it felt a lot like that. Yeah. Anyway,
I think maybe that time it spread. I mean, the area Persia had, because Spain is also close, the lower, I mean,
correct. The med kind of thing. Because there's so much of transfer of knowledge. And some of these patterns looked so, so much like Islamic patterns. So I thought maybe Persia would have led the way in some century.
Yeah.
All right.
Any like if any of you teachers are planning to want to do this tessellations, anytime, I can help you with the material or any kind of information. It's really nice to do with the children.
All right. Sendil, now it's you.
Thanks, Mama. That was so nice. So without much, we'll take the sheets and go straight to slide by slide. There are instructions, so we'll see what we are getting into. Be ready with the sheets. First A4 sheet, and we'll go straight. The first one. Set. Okay, I'll also stop my video. Choose which one. No. Okay. I'll also keep my video on for this. Okay, the first is, let's make a square out of this A4 sheet. All of you, can you also try and turn on your videos so that it's
really. Every one of you can pin Sendil and put it as the only element in your screen along with the presentation. Then we can see a live demo of what is being shown on the slide.
And I would really request everyone to try it so that it becomes easier for you to get a hands on. So I have this. Shall we go on to the next one? for this boat meeting. This is the boat which we have been doing in all monsoon season, and I'm in no doubt that Bangalore can have this in this time, but it's
Don't rub it in.
not a situation, but it's quite a sad one. But yeah, I understand what's happening there. Yeah. So we open this up, and then you start making into one fold, half of it. That's the next. Keep this piece. This piece is required. Don't need to throw it away. So, but we'll work on this. We also make this. Yeah. And now we have 4 leaves, 1, 2, 3, and 4 leaves. So you can either take 1 or and leave the 3. And now we are going to fold this. I'm just taking the first leaf alone on the 4. And turn it upside down and fold the other 3. So these creases are important as we do. So we've done this. That's in the next slide. So now once we have done this, here you can see a pocket, right? Once you have done, you see this pocket. That's what is there on the slide on the right side. So open this pocket and sort of make it into a diamond shape. There, get this. So we can go on to the next. This is pretty much now, if you open, you get this sort of, you can open this and then you can see a boat. So this is a traditional one, which we all would have done this. Sure. So now this boat is done. Now we unfold this whole thing. Go back to the first place and start unfolding it carefully. Carrying it. So we all have as many small pieces there. So now we can choose any piece and we'll choose this one. Look at this triangle. Yeah. So I'm just looking at one triangle from this, just as it is marked on the sheet. And looking at this triangle, I'm just going to mark this as a, okay. So the next is, we are trying to derive the Pythagoras theorem from this. So here we see 2 triangles here, one here, and then it's 1, 2, and then 3 and 4. You see the 1 and 2 on one side and 3 and 4 on the adjacent side. And now we look at the hypotenuse side. We see those 1, 2, 3, and 4 all together on the other side. That's 1, 2, 3, and 4. And if we have this as A, B, and C, that gives us that AB square plus BC square is equal to AC square. It's quite easy to remember. And while doing this, we can just allow the children to do the boat, and they come back to their memories from kindergarten in grade 6, as they do grade 6, grade 7, and then when they open and do it, it's so lively for them to come back to this. Go on to the next. So now we have this piece.
Senthil, a quick question.
Yeah.
Do you start your Pythagoras theorem like this itself, or do you introduce Pythagoras in some other way and come back to this one?
No, we do introduce the Pythagoras through some other ways, but this is in a class. When you start making this board, don't tell that, oh, we are going to do Pythagoras theorem, so let's do this.
Understood.
This could be this can be something like, can we look at this triangle, and they themselves can explore these things. Oh, what's happening here? What's happening here? And they can tell, oh, this looks pretty much like a Pythagoras theorem. So we can bring like that to that.
Got it. Thank you.
So now let's look at the piece which we have cut down. So we are going to look at the exponents. So this is the piece which was left out of the square from the A4 sheet. So I'm going to make the first fold. That's my first one fold. I got two portions, two partitions in this one fold. And let me make one more fold. So for two folds, basically, I got four partitions, like 1, 2, 3, 4 pieces for two folds. And let's make another one. This time, this way. This is my third fold. I got 8 pieces, 1, 2, 3, 4, 5, 6, and 7. Let's see if we can make one more. And that, when I unfold, that was my fourth fold. And I already see 1, 2, 3, 4, 5, 6, 7, 8. It's up to 16 pieces. So with this, move on to the next line. I went on to make one more fold. That was the last one. It's very difficult to go now itself. It's a small sheet. And with this, we can see for the fifth fold, we got close to about 32 pieces, all of it put together. Now we start listing them down. So as we list them down, you put a table, tabular column, go on to the next slide. And in that slide, we put a tabular column and say, what is the fold of number? And then what are the divisions we get? And how can it be represented in twos? And that's basically for the first fold, we got 2 divisions, which is just 2 or 2 to the power 1. And represented in twos, if we look at all of them, so for 100 folds, you would have got 2 power 100 divisions. So that's what it means. Now, as we have represented in twos, we go next step and then write into the exponents itself. So all this is great. There is one thing which is fascinating in this thing, which is the next slide. So for 0 folds, for no folds, initially, it is just one whole division. It's like one whole portion. That's what it is. So to prove to the power of 0 is 1 is just fascinating from this fold exercise itself. And then otherwise, it's not so easy to visualize to the power of 0, something to the power of 0 is 1. Like, how do we relate to that? And this exercise I felt personally so fascinating, and it just gave a quite a perspective from that exercise itself. Let's move to the next one. And we are going to make a tetrahedron with 2 A4 sheets. Keep the A4 sheets handy, 2. And here I'm going to fold it on the long side. And the next is I'm going to bring one of these edges and hold this one, and this edge should touch the middle line here. So that's on the next slide. And it should also fold from this corner edge here, and this is touching in the center. So we do this, and this is what I have. Is clear? Or it can look like this for you, something like this, with a fold from here. Okay, and the next is, so we take this sheet. So this is what I have, or it's like this. And then I take this sheet and fold it along this thing here. So you have something like a triangle with a little extra portion here, something like this. So you can fold that inside itself. You see that on the right side, there is a triangle with a little tail outside. So you can fold that tail within the triangle itself. Do you see that? Next line. So, and here we do see a crease here in the left side itself. Left slide, you see a crease where I kept my hand. And the next one, you fold the tail, and that crease is where we are going to fold in the next slide. Yeah, go to the next slide. Yeah, we saw that crease where it's near the thumb on the left side. And then, so in that crease, we fold it. Fold that inside, and the other also, we fold it inside. Creating all these things to come inside. And so this is how it is now. It is looking like a sort of a like a cup or something where all 3 sides are coming up. So something like this. So take another sheet. And so is that done so far, Ramesh? No. Yes. And then I'll do the next one also quickly. So first. Okay, so now these 2 are there. Move on to the next slide. You can see, yeah, so both of them should look like a triangle like this. Like if I fold all the sides, this should look like this, both 2 of them. Yeah. Now I have these 2 pieces. So one of them I can push it down, and the other is, so I put this extra little tail into this sort of pocket. And here, now when I fold this, I have something like a pocket here, like this. And on this also, I see a pocket on these two wings, like this. Can you see? It's like, it goes, one goes into this side and one goes into this side. So, next slide. So similarly in this, if I now, so what happens is now we have these two going into this. And this looks a solid tetrahedron. Yeah.
Wow.
It looks pretty solid actually. It is not light at all. And when it goes like an A4 sheet, if we can do this in a half A4 sheet, the smaller it is even more sturdy. Yeah. We'll look at one last thing. We're really running out of time, but yeah, we'll do a bird, which is
Not to worry, Sandil. You have 6 more minutes. Nikita is joining only at 6. So yeah, you're okay.
So I'm going to make a square sheet. Yes. Next slide. I have this fold now, which is a square. The next step is, so we'll make a half fold. From this half fold, open it, and then next step. So this edge, we are going to bring it to this half fold crease over here. So I'm bringing it here. Once we have done that, I'm going to bring this, the other side also, more like they've done something like a rocket or something. So bring this thing, it looks like a, or that bail over here, get a pocket or something like this. And now you also, the next slide. So this is what we have as of now. And next is we are trying to fold that into half. And once we have this into half, now we unfold that. So we have this. Now, one thing I would suggest is, if for some people you would have got, there are many lines which are moving from here. So I'll just mark those lines darker for you to see. Yeah, I'll just draw those lines. 1, 2. Okay, I'm drawing these lines, and then I'll also draw this side line also, this other diagonal line. Okay. Maybe it's too bright, but we can go on to the next slide. It will be clear in that slide. Here, yeah, we have drawn these lines in the slide. So, and then you start looking at the angles. It's here, it's since it's half of 90 degrees, the diagonal, that's 45 degrees. And you also know that the R1 is basically this is 45, and this whole thing is 90, and half of this is 45, and that has been divided into 3 segments. So this is 15 degrees, the first one here, and so this is 15 plus 45, that's 60, and so this is 120. Next. So since that is 45 degrees, the next is 60 degrees, and then moving on to the next, that will be 75 degrees. So it's just that the sum of these angles, these 2 angles on the outside, like 15 and 45, would become there as 60, and then 16 and then 60 and 15 would add up to 75 there, and 75 and another 15 would add up to 90. So you can also teach all these things outside to them. So it's nice to do this. And once we get all these things in place, then we go back to the continuing of from where we have unfolded this, we go back to that place itself. We keep closing it. Here you can teach the angles, some of those angles and other things, and you come back to this and then finish the bird as we have committed. So yeah. Can be anyways. The tail can be on either side. You can make a bird, and then like the tail can either be inverted or it can go on the outside. You can wish as you can do it, like however you wish, you can finish it. So have lots of fun with children while doing this, and then slowly bring the topics. The thing is, it's not about this is the only way, but these are things which I learned from VSS Shastri. He is in Kuppam in Kolar, close by, and he has done some fascinating things, as I've been talking about this Agastya International Science Center. So he has done these fascinating things, but the most important thing is this has motivated us to it motivates us to do much more and become innovative and intuitive in the class itself, and that's the main thing. So work with paper, work with your hands, and it will be quite a lot of work, quite a lot we can achieve in the class. Yeah, thanks.
Fantastic. It's really, really nice. I couldn't do the bird, but I did the tetrahedron at least. Last time I failed with the tetrahedron. This time I've got it. I'll show it off to my daughter.
Yeah, we wanted to do a workshop on origami separately, right? So yeah, we will do that after Dasara. I got a bit busy, so after Dasara we will definitely. And if Senthil can also join, it will be, whoever is interested, we can all do it together. It will be nice.
Yeah. If some of you found it a little fast, of course, somebody is saying they can't hear. Can the others hear? I mean, Mary, can
Yeah,
you
we
hear?
can, yeah.
Yes.
Yeah. Veena, it might be an issue on your side, Veena, but if you can't hear, Mary, if you can reply for Veena, please.
Yeah, sure.
Veena is saying she's having trouble hearing.
Yeah, I'll message her.
Oh, right. Okay, cool. Wonderful. This can be used for doing probability later. This can be a 4-sided die, and we can write numbers 1, 2, 3, 4, and later we can use it for probability, the tetrahedron. All right, great. Nikita, are you around?
No, sir. She's caught up in some emergency and she's trying to join through phone, but she's not able to join. Can we go ahead?
Sure. We will read out her case. So, Mary, if you can do the honors.
Sure.
We can get the summary of this whole thing. So, Mary, if you could just read it through, and we will then discuss it. Mama, you wanted to say something, Mama? You might want to be a little louder than your usual soft voice. So, because Nikita is on speakerphone and she has